A very good morning, students. Today we are going to discuss about the control hardware for temperature of living stream through the heat exchanger. So already we discussed the various component of the control system. Today we are going to discuss few more component of the control system where we are going to introduce a transducer and converter. So in this system, the control system required to control the temperature of liquid stream leaving the heat exchanger, which is shown into the figure. It consists of the following components. It consists transducer, which converts temperature signal to the current signal. Controller, which converts current signal to the current signal. Converter, which converts current signal to pressure signal. Control valve, which converts pressure signal to the flow rate of the fluid. So we are going to control the temperature of living stream from the heat exchanger. So how to maintain the temperature of the process stream leaving the heat exchanger is described in this control system. So how this system works? In this system, temperature of living stream from the heat exchanger is measured with help of the thermocouple, and these signals from the thermocouple is sent to the transducer, which produces an output in the range of 4 to 20 milliampere. So whatever the temperature measured by thermocouple, this temperature signal is converted into the range of 4 to 20 milliampere. Means if we take a range of temperature 0 to 100 degrees Celsius, then 0 means 4 milliampere and 100 degrees Celsius means 20 ampere. So if the temperature is in between, accordingly that much amount of current signals are generated, which is a linear function of input. The output of the transducer enters the controller, which is compared to the set point to produce an error signal. The controller converts this error to an output in the range of 4 to 20 milliampere according to the required value. Output of the controller enters the converter, which produces an output in the range of 3 to 15 psi, which is again the linear function of the input. Finally, the output of the converter is sent to the top of the control valve. So this is air to open control valve, where the flow from cooling water to the heat exchanger is taken place. So this is a diagram for controlling system of the heat exchanger. Thermocouple measures send signal to the transducer. Transducer converts this temperature signal to the current signals sent to the controller. Controller converts into the error in form of again electric signals. These electric signals are goes from converter to the control valve. These signals get converted into the pressure, and in air to open control valve, this pressure signal is get converted into the flow. So how much amount of water to be flow through the cell side of the heat exchanger is decided by the whole control system, and accordingly the temperature of outlet stream is controlled. Now consider how this process will be carried out. So consider initially the process is at steady state. The outlet temperature is equal to the set point. If the temperature of hot process stream increased, now if this process stream temperature increased, then what sequence will occur? The outlet temperature produces a proportional change in a signal to the controller. As soon as the controller measures this rise in the temperature relative to the set point, the controller output increases according to a proportional action, because this is a proportional controller. The increase in signal to the converter causes the output pressure from converter to increase the open the valve wider in order to increase the cooling flow rate. Increased flow of cooling water will reduces the process stream outlet temperature and will approach to the desired temperature. So this is how we can control the temperature of outlet stream of the heat exchanger. This different component of control system now can be applied to the any process from the chemical industries. Now very important to know about the control system is a controllers, which is a very important part of the any control system. So we will discuss about the controllers, what are their types, their transfer functions, and its application in the chemical industries. The various controllers are used in process control to convert the error generated in the range of 4 to 20 milliampere again to the current signal in the range of 4 to 20 milliampere and send it to the converter. Converter converts this current signal to the pressure signal and given it to the pneumatic controller. Various types of the controllers used in chemical process industries are on-off controller, proportional controller, proportional integral controller, proportional derivative controller, and PID controllers. We'll discuss these controllers one by one. On-off controller. On-off controller is a special kind of the proportional controller. It works only between the two extreme conditions. In case of control all, it works either fully open or fully closed. This is very simple one. The bandwidth of on-off controller is nearly equal to 0. So there is no bandwidth. Whereas proportional controller, in proportional controller, output signal is directly proportional to the error, obviously. So we can write P of t is proportional to epsilon t. So we can take its Laplace. Laplace will be P of s by epsilon of s is equal to Kc. So this Kc will be called as a steady state gain or is called as a steady sensitivity. And this is the transfer function for proportional controller, which can be shown through the block diagram as it is. Epsilon of s, Kc and P of s. So P of s by epsilon of s is equal to Kc. Now if the integral action is added to the proportional, it becomes proportional integral controller. So both actions are added. You can see proportional action where P of t is proportional to epsilon of t and integral action is P of t is proportional to the integration of epsilon of t. So you can combine together and you can find out its Laplace transform. So this is the way you can find out the Laplace transform for the proportional integral controller. It will be P of s by epsilon of s is equal to Kc into 1 plus 1 by tau is, where this tau I is called as a integral time. So earlier was nothing but only Kc. Now tau I is introduced here. So there are two parameters added. Tau I is integral time and Kc is a steady state gain. So this will be the block diagram for PI controller. The fourth type is proportional derivative controller. In this proportional, the derivative action is added as shown in the expressions. P of t is proportional to epsilon of t and P of t is proportional to the derivative action of epsilon of t by dt. So you can combine these two actions together and you can find out its Laplace. Its Laplace will be P of s by epsilon of s is equal to Kc into 1 plus tau ds, where one more term that added is called as a derivative time. So this is how this is a block diagram for the PD controller. Epsilon of s, Kc into 1 plus tau ds and right side will be P of s. Now the last type will be a proportional integral derivative type of the controller. So in this, along with the proportional action, the integral and derivative action is also added to the controllers. So these are the three actions shown. You can combine these three actions and you can find out its Laplace. The Laplace will be P of S by epsilon of S is equal to Kc into bracket 1 plus 1 upon tau is plus tau ds. So you can see the first term will be for proportional action, the second will be for integral, and the third term indicates a derivative action. So this is how you can find out the transfer function for the most important controller, that is PID controller. This will be a block diagram for the controllers. So the comparison between these controllers is shown in this figure. So this is how nothing but the control variable changes with respect to the time. Whenever there is no control, the first curve, the control variable continues to rise to the new steady state. So what happened in this case? That system reached to the new steady state and remains same, which is not desirable. So we are going to add a different types of the controllers. Initially, proportional controller. Because of this, the system is able to restrict the rise of control variable, and that is very important, and bring it to the rest. But again, the new steady state is reached. You can see curve 2. The difference between the new steady state value and the initial value is called as a offset. So it is shown here that proportional controller gives some offset. Generally, this offset is seen to be a 22% of its ultimate change. In case of PI controller, the addition of integral action eliminate the offset. You can see curve 3. So the offset is eliminated, but the disadvantage of proportional integral controller is the response become more oscillatory in nature. You can see. In PD controller, okay, they also provide the same offset like a proportional controller. You can see curve 4, okay, but the oscillations are decreased. So this response is non-oscillatory. So the last action is PID controller. In this, because of addition of integral and derivative action to the proportional action, it improves the response. The rise of this control variable is restricted more quickly. You can see the graph 5, and it rapidly returns to the initial value with less or no oscillations. And because of this reason only, the PID controllers are widely used in the industries. So now, if you want to select which controller is suitable for your system, you can consider the following parameters. If the offset of 22% is tolerable, you can use proportional controller. But if no offset is tolerable, but oscillations can be tolerable, you can go for PI controller. If offset is tolerable, but the oscillatory behavior is not desirable, you can go for PD controllers. And if you want everything to be in the limit, then PID controllers are widely used because of its fast response. So this is how nothing but various types of the controllers can be studied and is used in the industries. So at the end, we will discuss about the application of the controllers. These controllers are widely used in chemical process industries and allied industries for controlling the various parameters. Proportional controllers can be used effectively for the control of liquid level systems. Proportional integral controller can be used for control of vapor pressure and flow rates, in which undesirable offset is eliminated and accepted speed response is maintained. Proportional integral controller can also be used to control the temperature of the process conditions whenever offset elimination is essential. PD controller can be used for gas pressure control system in which less oscillatory response is desirable. PID controllers can be used for control of temperature and composition in which offset elimination is essential conditions and the faster response is desirable. Thus, PID controllers are widely used in industrial processes due to offset elimination and a non-oscillatory behavior. So this is how various types of the controllers are used in a chemical industries as per the requirements. In all these controllers, PID controllers are widely used because of less offset, less oscillation, and provides a quick response to the system. So this is how we can study the controllers with help of their transfer function, characteristics and applications. In next lecture, we'll discuss about the chemical reactor control system.